Hello, friends. It is Ben once again. This is a video for the differential calculus class. We are going to look at three things, which may seem like a lot, but it shouldn't be, okay? We're looking at Rolle's theorem, the mean value theorem, and the second derivative test. The reason why I have so much stuff lumped together there is that although Rolle's theorem and the mean value theorem are important enough that you should be exposed to them, there's not a lot of way for me to test you about them. So I will have an exercise or two in class for you to look at with them, but you know, the main thing for the day is going to be the second derivative test. All right. So let's just jump right into it. Assuming, of course, everything works. Go. Yay, it's going to work. All right, great. So Rolle's theorem, and it is not pronounced Rolle or Raleigh or anything like that. It's Rolle's theorem. Is a theorem that says if you have a function that goes up and then down, or down and then up, that somewhere along the lines it has to turn around and go back the other way, right? So the actual proof of this is based on the first derivative test and maybe dependent on the intermediate value theorem a little bit, but it is something that essentially guarantees us that we are going to have to get these horizontal tangent lines or otherwise have places where the derivative is not even defined at, okay? And the picture I drew for you here just says that because our function takes on the same y values at two different places, in between, you have to have at least one hump on it, but the particular one that I drew for you happens to have two more of them. And you can have a whole bunch more, right? But the theorem just guarantees you have to have at least one. So let's work through showing that this is true by just direct calculation on one of these problems. So we're going to be dealing with the function f of x equals cosine squared on 0 to pi. And I have set that up so that when you plug in f of 0, you're going to have the cosine squared of 0. Cosine of 0 is 1, so that's 1 squared. And then when you do f of pi, that's going to be the cosine squared of pi, which is going to mean that you have the minus 1 from the cosine of pi squared, which is also 1. Should have said equal 1 there. So since those two things are equal, somewhere between 0 and pi, there has to be a point so that f prime will turn out to be equal to 0. So f prime on this, we'll say 2 times the cosine of x, because the power rule says when you take the derivative of a square, you'll get 2 times the thing. But then the chain rule says you also have to put in the derivative of that cosine. And so we have minus 2 cosine x sine x, and we want to set that equal to 0. Now, I'm going to make a quick point here that this is minus sine of 2x, okay? That step that I just took there is taking advantage of a trig identity that if you haven't done trigonometry in a while, you may not remember, but trig identities are super important to a lot of things we do in calculus. So I'm kind of hoping that you all know that one. So what we're going to have to do here is to solve for when sine of 2x is equal to 0, okay? We could instead have done it at the other spot here of this cosine x 2x is equal to 0. Either one is going to work. What the heck? Let's go ahead and just do it with the cosine x sine 2x, cosine x sine x there. Because this tells us our two possibilities are either cosine x is 0 or sine x is 0. So then if we think about our unit circle, and that wasn't a very good picture of the axes, sorry. So on our unit circle here, if you pick out a point on it that has to do with an angle theta, okay, and then that point on there has coordinates cosine theta, sine theta. The place where the y coordinates or the cosine theta is equal to 0 are going to be at 0 and pi and 2 pi. So this sine x equals 0 part gives us x equal 0, pi, 2 pi, etc. But remembering that we're doing 0 to pi, those are the only ones we need to worry about. Okay. And then on the other part here, the cosine x being equal to 0, the place where the x coordinates are equal to 0 are going to be there on the y-axis. So that's going to be at x equals pi over 2 and 3 pi over 2. But again, we're only doing 0 to 2 pi, so we only have those two possibilities. So, oops. So the solution set that we would talk about here has 0, pi over 2, and pi in it. You know, just writing a list there. And the little e symbol means is an element of or is in the list. Okay. So we verified Rolle's theorem, and this is one of those where there's 3 different solutions. So you don't have to have more than one. We could have stopped as soon as we had one, but we got all of them. All right. Now, the mean value theorem is an extension of Rolle's theorem. What that means is that it is slightly more general, and it has a result that you don't have to have as many requirements for. In particular, you don't have to have f of a and f of b, the endpoints, having the same function value. So a lot of times people read this and put things together and say, oh, well, Rolle's theorem is just a special case of the mean value theorem. But the actual then way that somebody proved Rolle's theorem had to do with using, I said that backwards, but the proof of the mean value theorem, was based on Rolle's theorem. Somebody took Rolle's theorem and they made a new function, which was f of x minus m times x minus a, and used that to actually show this result here. So it's not that Rolle's theorem is a special case, it's that the mean value theorem is an extension. So that's a purely academic sort of distinction here, I suppose. But what it says for you is that if you have 2 points on a graph and you draw the line connecting them, that somewhere between those 2 x values, you're going to have a tangent line that's parallel to that. I guess you'd call this a secant line, and this is a tangent line. So somewhere there's going to be a place where those are parallel. And that turns out to be somewhat important to a proof later on of the fundamental theorem of calculus, which we don't get to in this class, but you know, it's good for you to have that information for later. Right, so we're going to verify this, which just means that we're taking a look at the function, and getting out what the x value is. So notice that the function I've given you, this x plus 1 over x, is not continuous everywhere. It's not continuous where x is 0. But fortunately, we've chosen an interval from 1 to 5, and that means that we do have it being continuous there. So we're going to take g of 1, and that'll be 1 plus 1 over 1, which is 2. And we're going to take g of 5, which is 5 plus 1 over 5, which I'll write as 26 over 5. And so now our g of 5 minus g of 1 divided by 5 minus 1 is going to be equal to 26 over 5 minus 2 divided by 4. And let's see, 2 is going to be 10/5, so that is 16/5 over 4, which is going to be 4/5. Okay. And now our g prime of x that we're going to set equal to that is going to be just 1 plus, now you got to think of 1 over x as being x to the minus 1 power. And then you can say minus 1 x to the minus 2 power, or in other words, 1 minus 1 over x squared. Okay, so we're going to set that equal to 4/5, and then we're going to solve. So if you subtract 1 from both sides, you'll have 1 over x to the 5th is equal to negative 1/5. I wrote a power wrong there, and I'm sorry. That was supposed to be 1 over x squared. That was just silly. So then if you cancel out the negative and take reciprocals, your x to the, I did it again. Man, your x squared needs to be equal to 5. So your x needs to be equal to the square root of 5. If you check, square root of 5 is, I don't know exactly, like 2.1, 2.2, something like that. But it's somewhere between 1 and 5. If you got a number that was outside that range, because like here you got plus or minus square root of 5, right? If you get a number outside that range, it's not what we want. So what we're getting for this is that f prime of square root of 5 is going to turn out to be equal to the 4/5. So really, the x equals square root of 5 is the one value in that interval that's going to give us the derivative we want. And that's all we're doing with this verification, is finding the value, right? Okay, so this is a little more convoluted here, and I accidentally put this onto your jams with a note that says, don't worry about actually working it out, but I didn't want to have to go back and delete it and change all the numbers and stuff like that. So anyway, we're going to use the mean value theorem, and we're going to show that anytime two functions have the same derivative, that they actually only differ by a constant, right? Well, yeah, this is something that comes up again later with the fundamental theorem of calculus, which is about taking antiderivatives. But again, a little past the end of this particular course because of the way the material is broken up. So what we're going to do here, remember my mention that the mean value theorem came from Rolle's theorem by just kind of constructing a special something or another. So what we're going to do is to take our h of x, and we're going to make it be equal to f of x minus g of x, okay? And then we're going to be able to say that h prime of x is going to be equal to f prime of x minus g prime of x, which, since f and g are always equal, is always 0, all right? But now if we take any A and B in the domain of, well, F and G, which is then going to be in the domain of H, then we can go ahead and say that we can take H of B minus H of A divided by B minus A, right? Now, I don't know what those values turn out to be, but I do know that because H prime is always 0, no matter what we choose, that this has to turn out to be equal to that H prime of X that's just this constant of 0. So this means H of A minus H of B, I wrote that backwards, but it doesn't matter, is always equal to 0. And thus H of A equals H of B. So that means that this function, H of X, is a constant. So H of X is some constant value C. And this means F of X minus G of X is equal to that constant value C. So F of X is G of X plus C, right? So if two functions have the same derivative, then they only ever vary by a constant. One of them is the other plus a constant. And if you're thinking, well, I don't see where that's super relevant to me. If you were to take a look here at the functions f of x equals sine squared x and g of x equals minus cosine squared x, and take their derivatives. So derivative of sine x will be, or sine squared x will be 2 sine x cosine x. And the derivative of this minus cosine squared x would be minus 2 cosine x times the negative sine x, and that'll cancel the minus out. And that shows that your sine squared and cosine and minus cosine squared differ only by a constant, which is, the constant is 1, right? And it turns out that a lot of these trig identities turn out to have something to do with that kind of thing, that you will have two functions that only differ by a constant, and that constant's determined by the trig identity. Okay, so all right, so here's the big thing for this particular assignment is the second derivative test. We did the first derivative test, and the thing that was going on with it was you found critical points. And once you had a critical point, you were able to test to see whether it was a maximum, a minimum, or neither by taking the first derivative and plugging in values on one side and the other side of those critical points. It could only change increasing or decreasing at a critical point. So for a second derivative, you have to take an extra, for the second derivative test, you have to take an extra derivative. But once you do that, you only have to plug back the critical point to it to check to see whether you got a max or min. Now, there are cases where you'll plug in f double prime and not get any information out of it. If, for example, here, I took my f of x equals x to the 4th, and take f prime of x equals then 4x cubed, and set that equal to 0, I will end up with x equals 0 being my critical point. But then if I do f double prime of x, I can see that that is 4x squared, and f double prime of 0 is 0. And that doesn't give me any information. But if you take a quick look at a graph of x to the 4th, it looks not exactly like a parabola. That is maybe too nice of a picture there. It looks like a it looks like a parabola that spent the pandemic sitting inside recording videos for calculus class. It's a little bit saggy at the bottom. Okay, yeah, sorry, that was maybe a bad metaphor there. But we actually have a minimum for the function. It's just that the second derivative test doesn't tell us that. However, if you have that situation, you can go try the first derivative test. So even when the second derivative test fails you, you can still classify something as a maximum or a minimum. It's just you have to go back and use the first derivative test instead. And the first derivative test is a little more time consuming, you know, but the important thing of that is don't just give up immediately, right? All right, so this one here, we're asked to find and classify any critical points of the function x cubed minus 3x plus 1. So first thing, we find the derivative, 3x squared minus 3. And we set it, well, first we look and see, is it undefined anywhere? Nope, turns out it's fine, that since it's a polynomial. And so you set that equal to 0. You can divide the 3 out and move 1 to the other side, and you end up getting x is plus or minus 1, okay? Once you have that, then we need to find out f double prime of x, which is just going to be 6x. So f double prime of positive 1 is 6, which is positive, okay? And so x equals 1 is a local, and you have to look back to see what the test said. Now, I'm bad at memorizing, so I always have mnemonic tricks to help me remember things. Here's how I remember this one. If you get a positive first derivative, you have a minimum because it looks like this. If you have a negative one, you have a maximum because it looks like that, right? So this says, since we have a positive second derivative, it's a local minimum, okay? You may also see answers written, I may do this myself sometimes, where they'll give you the x value and then the y value as well. And you just get that from plugging back in. What does that turn out to be? 1 minus 3 is negative 2 plus 1, so 1 negative 1, okay? Either way is fine, but sometimes if you had to answer this for like an automated system, you might have to give things in exactly the mode that they wanted them in. So for x equals negative 1, we end up getting a negative second derivative. So x equals negative 1. I think the point would be negative 1 comma positive 1, but is a local maximum, okay? Now, comment in passing. After you work out a problem like this, you might want to check from a graph and see whether your result is right according to a graph. But if you just draw the graph and don't do the second derivative test or the first derivative test, whichever's asked of you, if you just give a graph, you don't get the full points because the point is to use the derivative test that was requested. Okay. All right, let's do another one. So find and classify any critical points for sine cubed, and we're going to go from minus pi to pi. So usually we're going 0 to 2 pi. I just put minus pi to pi to make the point that it can be any period of this. Notice that since it's giving you an interval, you might think that it wants you to find extrema, absolute extrema for it. But anytime the instructions are find and classify any critical points, that means that it has to be something where you're talking about local extrema. Okay, find and critify, find and critify, find and classify critical points. Man, critify classical points. That is all right. So we're going to do g prime of x. And since the sine cubed, the power rule is on the outside, we'll have 3 times the square of the sine. And then inside that, the sine, the derivative of that is cosine x. Now we set that equal to 0, and that means we'll have to set each of sine and cosine equal to 0 and solve. Now, fortunately, we did that on a previous problem. And so 0, pi over 2, and pi were the things we were getting between 0 and pi. But it's going to turn out that since we're doing minus pi to pi, then we can just say plus or minus on these, okay, because of the way those are set up, okay? So now we're going to need g double prime of x. Oh no, that's going to be kind of messy. We can leave the 3 sitting out front. And you can think about this as being sine times cosine, right? So if you're taking sine times cosine, maybe I better write that out to the side, sine x, cosine x. You can think of that with the product rule and take the derivative of the first one, cosine x times sine x times cosine x, plus the derivative of the second one, leave the first one alone, and leave the third one alone, plus, and now we leave the first 2 alone, and take the derivative of the last one. Okay, that's pretty messy, but we can tidy it up without too much effort here. So 3 times, we had here cosine squared x sine x plus, and then the next one is sine x cosine squared x. And then the third one is minus sine cubed x, okay? So we can see that there is a factor of sine x for the whole thing. And then the first 2 are both cosine squareds. And then minus a sine squared x, okay? And I mean, you can make that even better if you really want to. But remember, all we're going to do is to plug values in, okay? So we're going to have to come along here and say g double prime of 0. And because sine x is in there, getting this to be 0, we're going to have the test failing for us, right? As a matter of fact, all of these where the sine of x is turning out to be 0, we're going to end up having this fail for us. So I'm going to write that in a simpler way and write g double prime of minus pi, g double prime of positive pi. Those are all equal to 0, so the test fails. And we'll just have to come back and fix it with the first derivative test, all right? So then we're going to try g double prime of the pi over 2, and then we'll do the minus pi over 2. And so we have 3 times the sine of pi over 2. So that is going to be a 1. And then 2 times the cosine of pi over 2 is 0, minus the sine of pi over 2 is 1 squared. So you have minus 3, which is negative. And that says that x equals pi over 2 is a local which? A local, now I got to draw it again, maximum, right? So I started writing minimum, but I would have been wrong. So I got to fix it. Local maximum. And then g double prime of minus pi over 2 equals 3 times the sine of minus pi over 2 is negative 1. 2 times the cosine of minus pi over 2 is 0, minus the sine was minus 1, but it gets squared. So we end up with a positive 3 out of this one. So x equals negative pi over 2 is a local minimum. Okay. All right. So what remains then is for us to talk about what to do on these where the test has failed. And I will erase my frowny face because that might worry us. I'm going to have to add an extra page on here. I don't think we'll use the whole thing, but let's go ahead and remember that we're dealing with this here. Come on. Sorry, y'all can't see it, but I've got the little spinny icon that says it's thinking. All right, so keep this in mind. And so we've got to think about our number line here. And our number line cuts off at minus pi and pi. And we know that 0 was another critical point that we have to worry about as well. But then minus pi over 2 and pi over 2 were also critical points. And we don't want to choose those as our sample values. So we're going to have to choose something like minus 3 pi over 4, minus pi over 4, and so forth. Okay, if you want to choose other values, you certainly can, right? So because we're maybe going to think about the x equals 0 here first, we'll do these two, and then we'll come back and figure out what to do on the others, right? So I'm going to have to get g prime of minus pi over 4. So 3 times sine squared. So sine of minus pi over 4 is minus 1 over root 2, or minus root 2 over 2. We have to square it, and then have our cosine. And our cosine of minus pi over 4 is positive 1 over root 2. So this will turn out to be 3 over 2 root 2, and it's positive. And now we're going to check g prime of positive pi over 4. Okay, if you're like me, I got that positive and I was like, yay, I'm done. But remember, first derivative test, we're going to have to do a little more work here. So 3 times the sine of positive pi over 4 is 1 over root 2. We're going to square it times, and the cosine 1 over root 2, and we get 3 times 2 over root 2, which is also positive. So this tells us that we have neither a maximum nor a minimum. Okay. So x equals 0 is neither a max nor a min. Okay. Gosh. So then we have to think about what to do with minus pi and pi. So the thing I'm going to want us to think about is treat minus pi and pi like they're the same value. Sounds weird, but because the function is periodic, the same things are happening at these two endpoints. So if I test 3 pi over 4 and minus 3 pi over 4, it's the same thing as doing 3 pi over 4 and then 5 pi over 4, okay? Or doing minus 5 pi over 4 and then minus 3 pi over 4. So we're going to check here. And the disappointing part is we're going to have the same thing happen. But, you know, play along a little bit here. So g prime of 3 pi over 4 is going to be 3 times. And then we have to say, what is the sine of 3 pi over 4? And that is going to be 1 over the square root of 2. Then we square it. What is the cosine of 3 pi over 4? Well, that is negative 1 over the square root of 2, which is going to be then negative 3 over 2 root 2, which is negative. And then when we do g prime of negative 3 pi over 4, and we're going to go through the same work. And get a negative number. And we find out that x equals plus or minus pi is neither max nor min. And I just totally messed up my grammar there because I shouldn't have said is, I should have said are. It's terrible to be all fussy like that, but you know. So if you took a look at a graph of these, the thing that's going on is actually that these are what is referred to as inflection points. They are where the concavity has changed. So it went from being concave up to concave down. So those happen at critical points as well. Doesn't always have to happen at a critical point, but it often does. So, all right, so the main thing to take away from this is that we can use the second derivative test, but if the second derivative test fails, as it did here, we have to turn to the first derivative test. And I should write down here, we used the first derivative test. And I'm going to erase this part about them being inflection points, because second derivative test gave no info. Right? Yay. So just keep in mind, if the second derivative test fails, we can always turn back to the first derivative test. It won't fail. So, all right. So the next one here, we're going to find and classify any critical points for x times e to the minus x. This will probably have less points for it. So h prime of x, we have to use the product rule. So 1 times e to the minus x plus x times e to the minus x, derivative of e to the anything is that same thing back. But then the chain rule says we have to take the derivative of the anything. And so this turns out to be e to the minus x times 1 minus x. So when you set that equal to 0, you cannot have the e to the minus x be 0. So we essentially rule that out and have that 1 minus x is 0, so x is 1. That's the only critical point. So that makes this a lot less work, right? Sure, a lot less than the previous one. Oof. But taking the derivative does require some more work. So we've got to look back here. And I always advocate factoring these things beforehand. It means you have to use the product rule like nobody's business, but it probably is a little bit less work in the long run. So product rule, we're taking the derivative of e to the minus x times 1 minus x. So the derivative of e to the minus x, we just found out, was minus e to the minus x. Leave the 1 minus x alone, plus e to the minus x times the derivative of 1 minus x is minus 1. So that is equal to minus e to the minus x, 1 minus x, minus e to the minus x. Well, I guess we can factor out a minus e to the minus x from it. And then you'd have 1 minus x and then plus 1. So minus e to the minus x times 2 minus x. That looks weird, but you know. But all we have to do is to plug in our value and have minus e to the minus 1. E to the minus 1 is like 0.35 or something like that, but it's a positive number. Remember, e to the minus 1 means 1 over e. It does not mean the negative of it, all right? But then times 2 minus 1. So we end up getting, well, that 2 minus 1 is just 1. So we end up getting minus e to the minus 1. So about negative 0.35-ish. But the main important is it's negative. So x equals 1 is a local, I have to think about this. It's negative. So you think about that figure with the sleepy eyes and it was sad. So this is a local maximum. And again, whip out a calculator or something, draw a graph of it and make sure, because if you get something where your two answers don't agree, you know, your graph and your second derivative test, something went wrong. Math is always consistent. So if something went wrong, I don't want you to feel bad, but it does mean that, you know, you copied a minus wrong or something like that. You just have to go back and correct it. Okay. All right, finally, we're doing this one here where we're going to look and classifying critical points for log x over x. So that one, we will do p prime of x. Oh man, quotient rule. I hate the quotient rule, but what you're going to do, you take the derivative of the top and then multiply by the bottom minus. Now we leave the top alone and multiply by the derivative of the bottom, and then the bottom gets squared. So we end up with 1 minus ln x all over x squared. Now, first thing you do is to see, is it undefined anywhere? Yes, it's undefined where x is equal to 0. So undefined where x equals 0, but that is not in the domain of our function. You can't take the natural log of 0 and you can't divide by 0, so we didn't have to worry about that. Okay. So what we really have to do is to take 1 minus log x over x squared and set it equal to 0. If a fraction is equal to 0, it's always the top that made it equal to 0. So 1 minus log x, 1 minus log x equals 0. Hey, if you notice, I constantly refer to ln x as log x, and that's because mathematicians don't really use the other bases. We tend to just use the natural log. I have all kinds of silly jokes about that being the simple life, where the mathematician is logging things in a natural way. But yeah, I know it's silly. But if ln x is equal to e, you take the exponential on both sides and then get your x is equal to e to the 1, or just e. All right, now that we have that, we're going to have p double prime of x. So we're going to have to do the quotient rule again, right? So we take the derivative of the top. So derivative of 1 is 0 minus the derivative of log x is 1 over x, multiplied by the bottom, minus, now we put the top down without the derivative, and multiply by the derivative of the bottom, which is 2x. And then we have to divide by the square of the bottom. X squared squared is x to the 4th. So let's simplify where we can. First simplification that I spot is that I can cross out an x here. And then the next thing, I think I better go ahead and rewrite a little bit first. So minus x minus 2x times the 1 minus ln x, all that divided by x to the 4th. I can see a factor of minus x that comes out of the whole thing there. And when I do that, I will have just a 1 and then plus the 2 times 1 and then the minus 2 ln x. Ugh, this was too far over the side. Let me rewrite that somewhere that is less messy. So this is equal to, what did we say? Minus x times 1 plus 2 times the 1 minus ln x. All of that divided by x to the 4th. And then let's cancel one of those out there so that it's a little bit less messy. And let's collect things together. So we'll have minus 3 minus 2 ln x all over x cubed. And I'm going to distribute the minus because that I think looks a little bit better. Okay. Did you have to do all that simplification? No, of course not. You could have just plugged in. But if you had to use it for something later, it might have been nicer to have simplified it. So 2 ln e, then minus 3, all that divided by e cubed. So the log of e is 1, so that means we have 2 minus 3 divided by e cubed, so minus 1 over e cubed, so negative 1/27. Doesn't matter, right? It's negative 0.0 something. And so that is negative. So x equals e is a local, let's see, negative, so it's a maximum. And that gets it for us, right? So second derivative test, you have to take a second derivative, but you get to plug in at just one place. So sometimes a second derivative test fails, not super often, but sometimes it does. And so you can always turn back to the first derivative test. Remember, don't just give up because you reach the second derivative test didn't work step. Okay, you can always go back to the first derivative. I won't give you a bunch of those, but you'll probably run into one. So, all right, see you all in class.